Now, since in the previous class we are discussing about the characteristic of the ring guard, and also I talked about the characteristic of the integer
Ramzan.
domain as well as the characteristic of the field too. Here in this particular class, I am going to do a few more problems, and this all these problems are actually very important for examinations point of view. So my next problem of today's second session of today's class is the following. Find the elements Find the elements in Z12. Now you know what Z12 is because I have explained this in the previous session, which are zero divisors. Which are zero divisors. And students, I must tell you that since I am doing this uh, problems for you uh, elaborately, but at the end of the session, you all of us know that for this particular semester we are all going to sit for the online examination or MCQ type of examination. You have given already one MCQ type of examination. In this MCQ type of examination, you have seen that questions of 1 or 2 marks are coming. 1 mark question means only simple answer, simple question, simple answer. 2 marks question means a little bit of mathematics is required. Although I am doing these broad questions, and I also know at the time of doing these broad questions that these broad questions are not coming in the way I'm doing it in the classroom. But if you cleverly think, each question which I'm writing right now, so for example, I am asking to find the elements in Z12 which are zero divisors. This question can also be set as as MCQ by putting several options. So you have to design the MCQ type of questions by yourself. Okay. In Z12, you are intelligent enough, you are matured enough, you will understand. I think you will understand what sort of MCQ type of questions can be asked over here. So in Z12, we see that what are the elements of Z12? Let us keep this in front of us. The elements of Z12 are this. Write all the elements, elaborate. Now look at these elements one after another. You will find that in these elements, you are going to find that if I consider the elements 2 and 6, if I consider the elements 2 and 6, this will give you the element 12, and which is nothing but equal to the class 0. If I consider the element 3 and 4, the class 3 and 4, this is also class 12, which is equal to 0. If I consider the element 4, 6, this is the class 24, which is equal to class 12, which is equal to class 0. If I consider 3 and 8, class 3 and class 8, this is class 24, this is class 12, this is class 0. If I consider 4 and 9, this is class 36, this is class 12, this is class 0. If I consider 10 and 6, this is class 60, this is class 12, this is class 0. I hope I have covered all the elements. And also we see that there exist elements like 1, 5, 7, 11, such that class 1 GCD of the greatest common divisor of 1 with 12 is equal to 1. Greatest common divisor of 5 with 12 is 1. Greatest common divisor of 7 with 12 is 1. Greatest common divisor of 11 with 12 is 1. Okay, and therefore you are not going to get this is not going to happen. This class 1 class 12 uh, if this is so, if the greatest common divisors of these elements are 1, so these elements 1, 5, 7 and 11, these elements are actually not zero divisors. So what are the zero divisors? Zero divisors are those elements. A and B are zero divisors. A is the zero divisor of 1. A is the zero divisor of B. If A is not 0, B is not 0. But here you see that these elements 2, 3, 4, 5, they are actually giving you the class 0. And therefore they will be the zero divisors. This all these elements, 2 is the zero divisor of 6, 3 is the sorry 2 is the zero divisor of 6, 6 is the zero divisor of 2, 3 is the zero divisor of 4, 4 is the zero divisor of 3, and so on. So all these elements, class 2, class 3, class 4, class 6, class 8, class 9, class 10, all these elements are actually zero divisors of 12. Now this particular question can be asked you in the MCQ type of question, and you can be given several options and to select the correct one from them. So you design, this is your task. I am giving it to you that you, each time I give you a problem, try to think about the question, try to think about a question which maybe can be asked from this particular problem that I'm doing right now. Say for example, this problem. Is there any integral domain? Is there any integral domain which has 6 elements? How can I do it? Is there any integral domain which has 6 elements? The proof of this result is a bit of tricky. Okay, but it is also very, the proof is also very interesting. If the trick is known to you, how to get into the solution, how to get into the proof, that will be, if you can feel it, then you will find it nice. Otherwise, if you think that this particular problems are liabilities, then you will never, you are not going to get it. You are not going to feel this particular problem. So for example, if I want to show that, if I want to verify that if can I obtain an integral domain which has 6 elements? Okay, so let us start with an integral domain. Let R be an integral domain. Okay, let R be an integral domain. And suppose the cardinality of R is equal to 6. R has 6 elements. Since R is an integral domain, it is obvious that R is a ring, and consequently R plus is a group. R plus is a group and is also abelian. Because it is ring, so R plus is definitely group, and not only a group, it is an abelian group. Because why? Because R is a ring. We know that every abelian group is cyclic. I proved this result in one of my classes. Every abelian group is cyclic. And so R will is generated by an element A belonging to R. Okay, so R is generated by an element, that is, we can write it as R is generated by this. This is the symbol of generator, you know very well. Now, if we consider, since every element of R is generated by A, if we consider the element twice A and 3A belonging to R, we see that twice A is non-zero element, thrice A is non-zero element, but twice A into 3A is equal to 6A square. This is 0 because the order of R plus is a finite group. So the order of R plus is 6. And therefore this will become 0. Some previous result I'm using, okay, from group theory, if you can recall. Thus, there is no integral domain. There is no integral domain with 6 elements. Why? Because we know that those rings are called integral domains. Those rings are called integral domains which have no zero divisors. Zero divisors means A not equal to 0, B not equal to 0, but AB equal to 0. That is called the zero divisor. A is the zero divisor of B, B is the zero divisor of A. But here it's not happening. It is not happening, therefore it has no zero divisor. And therefore R is there cannot be any integral domain with 6 elements. Next example I'm considering, example 3. Suppose R is a ring with identity. R is a ring with identity such that R has no zero divisors. Prove that 0 and 1 are the only idempotents in R. Can you recall the definition of idempotent? X is an idempotent if and only if x square equal to x. This was the definition. So let us consider an element A belonging to R such that S square equal to A. Then S square minus A is equal to 0, which implies A into A minus 1 equal to 0. Since R has no zero divisors, we have A equal to 0 or A minus 1 equal to 0. This implies the only possibility is A equal to 0 and A equal to 1, which proves the result. The only possibility is A equal to 0 or A equal to 1. Okay. Now, this type of problems, short problems that I'm doing right now, you are going to encounter in the examination. So keeping examination in mind, I'm showing you this type of short examples. Many more examples are there, but all examples that I will not be able to solve in the class because of the time constraints, you know. Here is another example. Let R be a ring with no zero divisors. Let R be a ring with no zero divisors. If A, B belonging to R be such that A to the power m equal to B to the power m, and A to the power n is equal to B to the power n, where m and n are relatively prime positive integers, then show that A is equal to B. Okay, how to prove it? Let us try to prove it. Since R has no zero divisor, if any one of A comma B is 0, if any one of A comma B is 0, if either A is 0 or B is 0, then other is also 0. So suppose A, B not equal to 0. Okay. Now since M and N are relatively prime integers, relatively prime positive integers. Okay. There are, since M and N are relatively prime positive integers, there are integers x and y such that mx plus ny is equal to 1. This is a very important result which we learned in school. It's from number theory. Very important result. It's a result not from group theory, it is a result from number theory. Okay. Let x greater than or equal to 0 and y less than or equal to 0. Why? Since m n greater than 0, neither x comma y greater than 0 together nor x comma y less than 0 together is possible. And then we can write it as a to the power mx equal to b to the power mx, which implies and b to the power 1 minus and y. because mx plus ny equal to 1. So here I'm using this result. Again, let us assume that a to the power minus ny and b to the power minus ny equal to c. Say, okay. So if it is so, then CA equal to CB. Why? Because I can write it as A into A into A to the power minus ny and B into B to the power minus ny. And since A to the power minus ny and B to the power minus ny, then I'm considering this to be this, they are same and they are equal to C. So we can write it as CA equal to CB. That is C into A minus B equal to 0. Certainly C not equal to 0 as A not equal to 0. We have already assumed over here, and R has no zero divisors. R has no zero divisors. Thus, A minus B is equal to 0. That is, A is equal to B as required. If we assume x less than or equal to 0, y greater than or equal to 0, the proof is similar. Similarly, you can build your logic. So these are some examples. These are some short examples which you can encounter in as an MCQ type of question in in the examination. Now I do not have much time, but quickly I am saying a few things about further discussions on ring theory. Just like when we learned set, and then there comes the concept of subset. We learned vector space. There came the concept of subspace. We learned group. Then the concept of subgroup came. Similarly, there are concepts of subrings and subfields. Okay, so all of these will not be, I shall not be able to discuss. Take any book and you can go you can study, if you want you can study these topics in detail, but since I have time, let us let me try to discuss the topic of subring at least. Okay, so what is subring? A non-empty subset, capital S, of a ring R plus dot is called a subring of R if S plus is a subgroup. S plus is a subgroup of the abelian group R plus, and S is closed under multiplication. S is closed under multiplication. That is, for all A comma B belonging to S, A B belonging to S. This is the definition of subring. I can show you one example at least. We know that capital R plus dot R is the set of real numbers. Is a ring. If we consider the set, Z root 2, which is a set containing in elements A plus B root 2 belonging to R. Actually, this is the set of surds, AB belonging to Z. Okay. Show that Z root 2 is a subring of R. Is a subring of R. So how to prove this result? Let us name this set Z root 2 as capital S for simplicity. Now, as 0 plus 0 root 2 belongs to R, where 0, 0 and 0, this 0 is for A and this 0 is for B. So I'm writing this A as this B belonging to Z. These are integers. So 0 plus 0 root 2 belonging to S, and hence S is not equal to 5. S is non-empty. So this non-empty part we have shown. If you can recall that if you want to prove that something is a subgroup, then suppose I'm considering, there was a theorem which I mentioned and I also proved in my class that if A and B belonging to, say, capital S, if you can show that this implies AB inverse belonging to S, then S is a subgroup. Okay, I use the symbol H to show the subgroup. A belongs to H, B belongs to H, implies that AB inverse belongs to H. I want to show that this S plus is a subgroup of R plus. So to show, if I go by the definition, since we have already shown that S is non-empty, next is to show that S plus is a subgroup of R plus. I can take the help of the given result. Then how? Let X comma Y belonging to S. I'm choosing two elements from S. Then X is of the form A plus B root 2. Y is also of the form C plus D root 2, where A, B, C, D, they belonging to Z. Now, X minus Y is equal to A minus C plus B minus D root 2. Why have I chosen X minus Y? Because whenever I'm writing A comma B belonging to H, implies AB inverse belonging to H. And since if the group is additive, the same result becomes A B comma B belonging to H implies A minus B belonging to H, because in this case, minus B is the inverse of, is the B inverse of B, because we are dealing with an additive group. So I'm choosing, whenever I'm writing X minus Y, actually it means if you want to stick to the notation, it means xy inverse. Y inverse is minus y here. So a minus c plus b minus d root 2, this belongs to S as a minus c comma b minus d belonging to Z. Thus S plus is a subgroup of R plus. And also, so second part is also proved. Last part is that we have to show that the thing is closed with respect to multiplication. Also, if I multiply the elements x, y, which is a plus b root 2 into c plus d root 2, after multiplication we will get ac plus ad root 2 plus bc root 2 plus 2bd, which can be written as ac plus 2bd plus ad plus bc into root 2, which obviously belong to S, as AC plus 2BD belonging to Z and AD plus BC belonging to Z. All the conditions of subrings are satisfied, and therefore therefore S is a subring of R. So the result is proved. Now, similarly, I'm giving you another example that I'm keeping for you to prove by yourself. The ring of Gaussian integers Zi is equal to a plus ib belongs to C, a comma b belongs to Z, I square is equal to -1 is a subring of C. Try to prove this result. Okay. And there are other results also. Many more results are there. For field, you can design the subfield also. And just like we learned about the concept of this coset and quotient group, similarly in ring also, you can consider a kind of set which is called ideal, which will play the role of coset in case of ring, and with these ideals you can form the quotient rings. Okay, but these discussions of quotient rings and ideals, these are not mentioned in the syllabus. So I'm actually a bit confused whether we need to discuss this particular thing in the class or not, because I haven't found any questions, any such questions so far. I have to ask other teachers what is their opinion, whoever is teaching in the information technology students, whether they are covering this quotient ring and the ideal section. If I see that in other classes, you also try to find it out, whether in other classes who are, say for in CSE section B, another teacher is teaching, and in IT, Kostov sir is probably is taking the class. So whether they are teaching ideal and quotient ring in the class or not, I'm also going to ask them. You also try to find it from the student, from your friends. So if they are covering these sections, then I'll also try to cover this section. But I think according to the syllabus, I think these concepts of quotient rings and this ideal is actually not needed for this course curriculum. So in next week, I'm going to start the last topic of this unit 4, which is called Boolean algebra. And with the Boolean algebra, I'm going to conclude this unit. And after that, we'll go to the section of graph theory. Now, my discussion about the class is over. But before you